You've probably looked in a mirror 1,000 times, right? Every morning, every bathroom break, every time you walk past a shop window. Your reflection always looks perfect, just as it should. Colors intact, your skin tone, your eyes, your clothes, all of it appearing exactly how it should be. A mirror, it seems, is just an object that reflects reality. You've never thought twice about it, have you? But wait. Pause for a moment. Think about the mirror itself, not your reflection, but the actual mirror. What color is it? Silver, right? That cool metallic gray you instantly recognize. But here's the question I want you to really think about. How does a piece of silver glass reflect all colors perfectly? It seems odd when you really stop to consider it. When you wear tinted sunglasses or look through colored glass, everything you see gets tinted by the color. That's how colored objects work. They impose their color on the light that passes through them or bounces off of them. So, why doesn't a silver mirror do the same thing? Shouldn't it reflect everything with a silver hue? Shouldn't your reflection have a metallic, grayish tint? But it doesn't. Your reflection remains perfectly colored, just as it would in any other reflective surface. This contradiction is what you never questioned, because mirrors have always felt normal. You've grown up with them. Your brain filed them under understood long before you were old enough to ask questions. But familiarity is not the same as understanding. You see, not being surprised by something doesn't mean you truly understand it. In fact, when something doesn't surprise you, that's exactly where the intriguing mysteries hide. Right there in the ordinary, in the things you see every day but never really think about. When you start asking questions about how a mirror works, about why silver looks silver yet reflects all colors, you begin to uncover something deep, something you never thought about before. And once you understand it, you'll see the world differently. It's not complicated. It's even more surprising. And once you see it, you'll never unsee it. Let's break it down, starting with what you think you know: light. You know that light is electromagnetic radiation. It's made up of different wavelengths, which our eyes perceive as different colors. Short wavelengths give us blue, long wavelengths give us red. You were probably taught that in school, but have you ever truly understood what happens when light hits an object? When light strikes most surfaces, atoms in those surfaces absorb certain wavelengths and reflect others. It's not magic. It's simple physics. Let's use an apple as an example. When light hits it, the apple absorbs certain wavelengths, like blue and green, and reflects only the red wavelengths. So, when you look at the apple, you see red, because that's the wavelength the apple reflected, and the other wavelengths were absorbed. This is how color works. Objects absorb certain colors and reflect others. The color you see is the light that the object didn't absorb. Simple, right? Now here's the catch. If that's how color works, why doesn't silver work the same way? Silver, as we know, is not on the light spectrum. It's not a color you can find in a rainbow. There's no silver wavelength in the light spectrum. When you look at a rainbow or through a prism, you see all the colors: red, orange, yellow, green, blue, and violet. But where's silver? It doesn't exist as a color of light. So what's going on when you look at a silver surface like a mirror? What is it reflecting, and why does it look the way it does? Here's where the real answer lies. It has everything to do with what makes metal, well, metal. Unlike most materials, metal has free electrons, electrons that aren't bound to any specific atom. They roam freely between the atomic nuclei like a fluid. This is what makes metal so special. It's what allows metal to conduct electricity and also to be shiny. When light hits metal, it doesn't just bounce off the way light interacts with ordinary objects. Instead, the oscillating electric field of light pushes on the metal's free electrons, causing them to move and oscillate at the same frequency as the incoming light. Red light comes in oscillating at a red frequency, and the electrons oscillate at the red frequency. Blue light comes in oscillating at a blue frequency, and the electrons oscillate at the blue frequency. Here's the twist. Those oscillating electrons act like tiny antennas. And what do antennas do? They radiate. They send out electromagnetic waves. So, as the incoming light is absorbed by the metal, those electrons re-emit it in all directions, including back the way it came. This is what creates the reflection, and this is what makes silver look the way it does. Silver, unlike other materials, doesn't absorb any specific color. When light hits silver, all the colors are reflected equally. Red, orange, yellow, green, blue, violet. Every color bounces back in the same amount. Your eye doesn't see a specific color because all colors are reflected equally. So you perceive it as neutral, gray, metallic, what we call silver. Now, you might be wondering why other metals, like gold or copper, don't look silver. That's because their electrons respond differently to light. Gold, for example, doesn't reflect blue light very well. Instead, it absorbs it and reflects more red and yellow, which is why it has a warm, distinctive color. Copper behaves similarly. The color of a metal depends on how its free electrons interact with different wavelengths of light. Silver and aluminum are the neutral metals that reflect all colors equally. So when you look in a mirror, you're not seeing the reflection through any mysterious or magical process. You're seeing light that left your face, traveled across the room, bounced off a sea of free electrons, and then was sent right back to your eyes. The mirror doesn't know what color things are. It doesn't preserve an image through some clever trick. It's simply electrons doing their thing, responding to electromagnetic fields. The perfect reflection you see is a consequence of physics, not design. Every time you look into a mirror, you're not just seeing yourself. You're seeing the electromagnetic interaction at play. You're witnessing physics unfold in real time. And now, every mirror you look into will make you aware of the fascinating, simple physics that's making it all possible. If you've learned something new today, and if you want to understand the world in a way that goes beyond surface-level explanations, subscribe to Feynman Physics. This channel is all about diving deeper into the real science behind the things you think you already understand. Every subscription helps me keep this channel alive, continuing to break down the misconceptions and teaching you how the universe actually works. Subscribe now, and let's keep exploring the amazing world of physics together. Now that we understand why silver looks silver, let's take a deeper dive into what's actually happening when you look at a mirror. When you look at any reflective surface, what you're really seeing isn't a picture of reality. It's a model created by your brain based on a very specific set of interactions. You're seeing the result of light interacting with electrons on that shiny surface, and that interaction is what creates the image you perceive. Let's slow down for a second and talk about light. What is light really? Most of us have a basic understanding of it. Light is that thing that lets us see, that travels from the sun to Earth and illuminates our world. We know light is made up of electromagnetic waves. Different wavelengths of light give us different colors. Shorter wavelengths are blue, longer wavelengths are red, and everything in between makes up the full visible spectrum. But light isn't just a wave. It's a part of the electromagnetic spectrum, which also includes radio waves, microwaves, infrared, and even X-rays. When we talk about light, we're referring to a very specific type of electromagnetic radiation, the part that our eyes can detect. So when you look at a mirror, you're seeing light that's bouncing back at you. But what's happening on a deeper level? When light strikes the surface of a mirror, it's not just bouncing back off the glass like a ball hitting the floor. At the most basic level, the light is interacting with the electrons in the mirror. A key difference between a mirror and other surfaces is that the mirror has free electrons that aren't tied to any specific atom, unlike materials like wood or fabric, where the electrons are more confined. In metals like silver, those electrons are free to move around, creating an interaction between the electromagnetic wave and the free electrons that leads to light bouncing off. Think about this. Light is made up of oscillating electric and magnetic fields. When light hits a reflective surface, it creates an oscillation in those electrons. And just like a wave in the ocean, these electrons move in sync with the light wave. The oscillation of these electrons then radiates out. Some of it goes through the surface, some of it bounces back. This is where the magic happens. When you look at a mirror, you're seeing the light that has been reflected back toward your eyes. And because of the way the free electrons in the metal surface behave, the light is reflected in such a way that it maintains its original color and intensity. No colors are absorbed, and no frequencies are distorted. All the light that hits the mirror is reflected, creating the perfect replica of whatever is in front of it. Now, let's zoom in on how a mirror works in practical terms. The surface of a mirror is incredibly smooth, which is a key factor in producing a clear reflection. This smoothness ensures that the electrons can react uniformly to the incoming light, causing it to bounce back in a coherent and organized way. If the mirror's surface were rough or uneven, the light would scatter, and the reflection would be blurry. But a well-polished, flat surface like that on a mirror keeps everything aligned, reflecting the light coherently and giving you a crisp image. But here's where things get interesting. While mirrors are great at reflecting light, they're not perfect. They don't reflect 100% of the light that hits them. In fact, most mirrors only reflect about 90–95% of the light, with the rest being absorbed or scattered. So when you look in a mirror, you're not seeing a perfect reflection of reality. You're seeing a slightly diminished version of it, but this small loss of light isn't noticeable to our eyes. Why does this matter? Because it highlights something important. Every mirror, every reflective surface is not just bouncing light back at you. It's doing so in a way that's influenced by the material's structure and the properties of the electrons within it. These electrons have a fundamental role in how light behaves, and their free movement is what allows the mirror to reflect light without distorting it. It's all about how the material interacts with the incoming light, how it's able to reflect all the colors equally, and how that process makes the image we see in the mirror. So next time you look in a mirror, don't just see a reflection of yourself. See the physics at work. The dance of electrons, the oscillating electromagnetic fields, the way light is manipulated to give you a perfect replica. It's a simple concept on the surface, but the deeper you look into how light interacts with materials, the more fascinating and complex it becomes. What seems like a common, everyday object, something as mundane as a mirror, becomes an entry point into the wonders of light, metal, and the forces that govern the universe. And when you truly understand this, you realize that the world around you, even the things you think you already know, is far stranger and more intricate than you've ever imagined. Everything, from mirrors to metals, from gold to glass, carries with it the beauty of physics in action. And all of it starts with the simple, yet profound, interaction of light and matter. Now that we have a basic understanding of what happens when light interacts with a mirror, let's dive deeper into how the properties of different materials influence how they reflect light. We've already discussed the role of free electrons in metals like silver, which allow them to reflect light in a perfectly equal manner. But this principle doesn't apply to every material. The way light behaves when it encounters materials like gold, copper, or even water is different. Take gold, for example. Why doesn't gold reflect light in the same way as silver or aluminum? The reason lies in how gold's electrons behave. In metals, the electrons that are free to move around create a sort of sea of charge. But not all metals are created equal. Gold's free electrons have a different response to certain wavelengths of light, particularly blue light. Gold's electrons absorb some of the blue wavelengths and reflect more red and yellow light. This is why gold has that distinct warm, reddish hue. It's reflecting primarily those colors while absorbing the others. On the other hand, copper behaves similarly but with even more pronounced color shifts. Copper's free electrons absorb a lot of blue and green light, reflecting mostly red and orange. This is why copper has a characteristic reddish-brown color, which is different from gold's warm shine. These differences arise because of the way each metal's free electrons respond to the light's oscillating electric field. The takeaway here is that the color of a metal is directly tied to the frequency response of its electrons. Each metal's electron sea interacts differently with the light that hits it, making each one unique in the way it reflects and absorbs various colors. But in the case of silver, its electrons are what we call non-selective, meaning they reflect all wavelengths equally. This is why silver and aluminum are considered neutral metals. They reflect light in a way that doesn't impose a particular color on the light they reflect. This non-selectivity is what allows silver mirrors to give you a perfect, full-color reflection. When you look at a silver mirror, what you're really seeing is light that has been reflected back to you without any of it being absorbed or altered in any way. Your reflection appears normal, as if it's been transmitted through the glass, but what's really happening is much more complex and fascinating. It's not magic, it's pure physics, the fundamental behavior of free electrons reacting to light. So, what happens when you see your reflection in a mirror? It's an amazing display of physics, of light interacting with metal at the quantum level. You're not just seeing your physical self, but also the beautiful, intricate dance of photons and electrons that's constantly happening all around you. So now, we can see that a mirror, at its core, is a perfect reflection of light due to the behavior of free electrons in metals. But let's step back for a second and look at what this means in a larger context. You've been interacting with mirrors your entire life, looking into them daily without thinking twice. But now, armed with the knowledge that you're looking at a highly sophisticated interaction between light and electrons, the very concept of a mirror seems to transcend what you thought it was. This simple reflective surface is actually a direct manifestation of fundamental physical processes. Every time you glance into a mirror, you're not just seeing your reflection. You're witnessing the elegance of light's behavior, electrons' actions, and electromagnetic principles at work. But there's still more to explore here. If mirrors are just reflecting light based on how free electrons and metals react, what happens when we look at non-metallic surfaces that still appear shiny, like water or glass? These materials don't have the same free electrons as metals, but they can still reflect light. The process here is a little different, but it's still based on the fundamental principle of light interacting with matter. Take glass, for instance. Glass is not a metal, so it doesn't have the same free electron sea that metals like silver or aluminum do. However, glass has electrons that are bound to atoms, and when light hits the surface, it excites those electrons, causing them to oscillate. Unlike metals, though, the electrons in glass don't have the ability to move freely through the material. Instead, they move locally within the atoms or molecules. The oscillations of these electrons cause the light to be partially reflected back off the surface and partially transmitted through the material. The light that passes through the glass then refracts, bending as it moves through. This is why you get a reflection when you look at glass, but also why you can see through it. It reflects some light, but it allows the rest of it to pass through. The amount of light reflected versus transmitted depends on the angle at which the light strikes the surface and the material's properties. This is the reason that glass windows reflect some light but still allow you to see through them. Water, too, behaves similarly in terms of reflection, but with water, the reflection is more pronounced, especially when the surface is still and calm. Water molecules also have free electrons, though not in the same way metals do. The water's electrons respond to the electromagnetic waves of light, causing a partial reflection on the surface. The rest of the light passes through, which is why you can see through a body of water. When you look at a calm pond, for instance, you see a reflection of yourself in the surroundings because light bounces off the surface and reflects back to your eyes. At the same time, the rest of the light passes through the water to deeper layers. It's important to note that with water and glass, the quality of the reflection you see is influenced by the angle and smoothness of the surface. In metal mirrors, the surface is meticulously polished to a perfect flatness, which allows the reflection to be sharp and clear. But with water and glass, the surface imperfections or the angle at which you view the surface can cause distortion or reduce the clarity of the reflection. Now think about all these materials: metals, glass, and water. What they all have in common is that light behaves predictably according to the underlying physical principles, but they each express this behavior differently based on their structure and properties. This is what makes the study of light and reflection so fascinating. The same electromagnetic principles are at play everywhere, but how different materials interact with light can create dramatically different effects. In fact, even the most ordinary things around you, your smartphone screen, the windows in your house, the water in a glass, are all intricate results of these same physical processes. You're constantly surrounded by reflective surfaces, and now you can see that what you've always assumed to be a simple interaction, light bouncing off a surface, is actually a complex dance of energy and electrons. From the polished metal of a mirror to the smooth glass of your window, each surface behaves according to the same fundamental rules, but the outcome is never exactly the same. So, next time you look into a mirror or at any shiny surface, remember, you're not just seeing your reflection. You're seeing the intricate interactions between light, electrons, and materials. It's physics in action, something so beautiful, complex, and fundamental that we've been overlooking it for centuries. The simplest objects you encounter every day, like a shiny spoon or a glass of water, are demonstrations of some of the most profound principles of physics at work. And it's this understanding that allows us to build technology, create art, and even understand the world on a deeper level. You now know that the mirror you've been looking at your whole life is far more than a simple reflective surface. It's a window into the fundamental workings of the universe, showing you the incredible dance of electrons and light that makes everything visible to you. It's a testament to the beauty and depth of the physics that shape our reality. And if you really start thinking about all the things we interact with every day, you'll realize how much more there is to discover in the most ordinary aspects of life.